In this episode, the world's urban railroads. The unique challenges of laying tracks in the city.
To do 2,500 blasts under Grand Central required a lot of coordination to make sure that we didn't disturb anything above us.
And the ingenious solutions.
This port is just such an impressive operation, and the whole thing is running on rails.
Without the cable cars, it would be really difficult to get around.
To make the impossible possible. Despite being able to weave their way across the planet, covering colossal distances on cross-continental journeys, trains are in a league of their own when serving the world's cities. Many of our busiest metropolises thrive on the existence of the railroad. Transporting the population on its daily commute, getting goods to market, and visitors to great landmarks. But the urban environment poses some remarkable challenges for railroad engineers. From grueling inclines,
You can see the challenges that are faced, and as you can see the undulating territory and how steep these hills are.
to keeping supply on par with demand.
Our biggest challenge is the new generation of vessels. And it's one challenge to work the vessel, other challenge to get them into the hinterland.
And delivering vital services.
The post office was going to have to find a faster and more efficient way to get that mail around town if the capital was going to stay connected.
And it's one such seemingly impossible challenge that has been facing engineers in New York for decades. New York City, a metropolis that relies heavily on its railroads. With around 90 million passengers a year traveling westward from Long Island to the heart of the city, Manhattan, the busiest commuter line in the U.S. is desperately overstretched. To relieve the strain, engineers and construction workers are at work in the central hub of the city's rail network, although few passersby would even notice.
So we're here in the heart of Grand Central Terminal. This is where hundreds of thousands of passengers a day come through to take the trains.
Mike Pujak is part of a team working in near secret to solve New York's commuter problems.
Given how packed and congested Midtown Manhattan is, we have to work like a stealth project. All of our materials and all of our equipment still, to this day, has to come in from Queens and the Bronx to feed this job.
Despite the challenges, the city's non-stop transit system is operating undisturbed.
It's remarkable that hundreds of thousands of tourists and commuters come into Grand Central every day, into this iconic structure, and don't have any idea of the magnitude of the construction that's going on right below their feet.
The East Side Access Project, with ambitions to completely transform the transit network in New York, it's an undertaking on a truly grand scale.
This is one of the largest infrastructure projects ongoing in the U.S. right now. This is incredibly important for New York. This project is $11.1 billion, and we have right now currently about 1,600 people working on it. And at one point, we peaked out at 2,600 people a day working on this project.
Connecting one of the world's largest railroad commuter stations with the busiest commuter railroad in the U.S. via more than 7 miles of tunnel, East Side Access will carry trains along a network of new and refurbished tunnels into a 4-platform, 8-track terminal directly under Grand Central Terminal and Park Avenue. It's a giant space that must be constructed from scratch. And that's easier said than done when you're operating under some of the most expensive real estate on the planet.
So we're in the East Side Access Caverns here, and we're 150 feet below Park Avenue and Grand Central Terminal. if you don't carefully plan what you had to do down here, you will wind up creating a situation where you could disturb the ground because it could influence some of the structures above.
With the consequences of any errors adding to a potentially multi-billion-dollar disruption, it's a scenario that had to be avoided at all costs.
We could not interrupt this economic area and the traveling public coming into Grand Central, because that's a lifeline for the economy in this area.
To create this vast underground terminal, Mike and his team utilized an appropriately awe-inspiring solution.
Just to set the stage here, this is all Manhattan bedrock. There was nothing here. And then we used drill blast methods to basically carve out the balance of the structure. It's controlled blasting. And so you basically calculate the amount of powder you're going to use to control how much rock you want to remove. And then you measure the vibrations so that way you don't impose any issues to the buildings and the structures above. When finally excavated, this space was 1,150 feet long, which is larger than the Chrysler building is tall, and it was 60 foot high by 60 foot wide, and we have 2 caverns. I mean, to do 2,500 blasts under Grand Central and not impact them required a lot of coordination with Metro North.
Work on this supersized city railroad began in 2007 with the launch of a pair of giant tunnel boring machines under Manhattan. Using powerful cutting heads to burrow through the layers of dense rock, the tunnel boring machines were set on course towards Grand Central. As tunnel engineer Jeff Rice recalls, operating in the heart of New York caused complications.
We were in a burgeoning city somewhere where there wasn't already an overfilled Penn Station and a historic Grand Central in the way, completely developed Manhattan. Heavily traveled train traffic areas and within the project limits, the project would have been much simpler.
The huge volumes of rock and debris generated by the tunneling process made removing it a challenging logistical dilemma.
Since we couldn't bring muck up through Grand Central, and it was not viable to bring it up by train out of Grand Central, we needed to bring it out where it could be handled for trucking.
With working out of the overcrowded center of Manhattan out of the question, the team had no alternative but to take the wreckage the long way around.
The rock removed from the tunnels was then brought back entirely through the second tube of the existing tunnel on a conveyor system out to Queens. The sheer volume of rock that was removed for the length of all the tunnels, it's time-consuming.
Stretching for over 1.2 miles, the giant conveyor fed out to a construction yard where rubble was loaded onto trucks.
Thousands of tons of material was brought out. The tunnel has become pretty much a highway for all the resources in and out of the tunnel.
But one section of tunnel under Queens poses East Side Access's engineers with a particularly tricky set of problems.
There you go.
With soft ground, a high water table, and dense active city infrastructure to contend with, inspired engineering solutions are required.
What we're approaching is one of the greatest challenges on the East Side Access project is the Northern Boulevard crossing. As you can see, Northern Boulevard at midday is still a heavily traveled truck route. Here comes a Astoria Line train on the elevated structure. On top of the elevated structure and Northern Boulevard, underneath Northern Boulevard is a 5-track subway structure, one of the heaviest traveled lines in all of New York City.
To get the trains for East Side Access to their destination, the route must cross directly below these 3 major transport links. But the challenging ground conditions leave only a small area of viable material to tunnel through, and little margin for error.
All the traditional methods, and particularly methods that were tried and true here in New York City and in North America in general, they met defeat. We didn't want to do something innovative. We had to do something innovative here.
With just under 10 feet of soil between the subway and the new tunnel, the engineering required to solve this problem had to be bold.
This is one of, if it's not necessarily the first, but this was the first time for a tunnel in North America where we were able to horizontally freeze the ground. Freeze pipes basically carried tubes that ran back and forth to a freeze plant. The freeze plant used a chilled brine to pump the chilled brine through all of the pipes individually and freeze the ground slowly.
Creating this frozen layer of earth helped to strengthen the ground sufficiently to tunnel in safety.
The frozen arch performed better than we expected. That provided the initial support to allow us to actually perform our sequential tunneling. It very high stakes, but in the end, it was a very big success, and very proud of it.
Work to complete this railroad is ongoing, but East Side Access will also need to be able to handle a horde of New York commuters. Moving thousands of people from the train tunnels below up to ground level would take an engineering solution on an epic scale. New York's East Side Access project will increase city access for thousands of commuters. It will also drop them off in the heart of Manhattan, around 15 floors below ground level.
In a peak time frame when this job is running, Long Island Railroad plans to move 24 trains an hour into the terminal. And that's adding a lot more people down below, 150 feet below Park Avenue, that have to get out to the street. And with that, that'll be 160,000 people that have to be moved. And we needed to figure out a way to do that.
The answer, as with all things on this impressive urban project, is on an enormous scale.
We have 17 high-rise escalators altogether that will head down to the caverns below. They're 90-foot high escalators, and when they're completed, they'll be the longest escalators in New York City, and some of the longest in the country. At a 150-foot run, these are some massive escalators that are being constructed here to connect the concourse with the caverns down below. Right now, we're rigging in one of the truss sections, so the escalator comes and putting it on the incline, and then they'll bolt it up together, and then they'll install the next one. You're working on 30-degree slope, so everything's cabled back and winched back, and they use a whole bunch of chain faults to lower these things safely into place so they can interlock them and go to the next unit.
Huge volumes of passengers are expected to flow into the new terminal each day, so the efficient movement of people will be essential to the project's success.
We're heavily relying on passenger flow, utilizing these banks of escalators. These are what will be the main feed of bringing everybody up from the caverns or down to the caverns, up to the concourse level, to the street, and into Grand Central proper itself.
But simply getting these giant escalators below ground has been a challenge in itself.
The contractor has no access from Manhattan to build out this job, which is kind of unique. We couldn't come into the middle of 42nd Street and Midtown and just start taking out, and doing an open cut. We had to bring in everything from a remote area, from Bronx, on work trains, just to access this.
It's another epic achievement in a project that, once complete, will stand amongst the most impressive feats of urban railroad infrastructure anywhere on the planet.
Everything on this job is larger than life. The tunnels are more difficult than the usual tunnel. The soil conditions have been more difficult.
And despite all the obstacles, the goal is to unveil East Side Access to the commuters of New York in 2022.
When this is done, we're going to greatly improve the access to New York City for riders from Long Island. It is a significant achievement.
Thanks to the hard work of Jeff, Mike, and many more like them, the city will soon be able to rely on another impossible railroad.
It's personally rewarding to work on a project this long and know that it's going to be around for generations to come and really change the infrastructure in Manhattan.
Trains have to contend with all manner of obstacles in cities.
Hey, come on!
But when it comes to getting people from A to B, inclines can feel like an incredible challenge. Both man and beast can struggle to overcome slopes, but trains can simply run out of steam. In California, railroad engineers had to find a way to keep a train running on some of the steepest city inclines imaginable. San Francisco, notorious for its hilly geography. Historically, horse and cart were used to climb the streets. But accidents were common and often fatal. A daily challenge that local Ed Cobean knows all too well.
Just imagine these streets being cobblestone, and with the fog or the dew or the mist or the rain, when you get a wet cobblestone and how steep these hills are, how would those horses be able to get up pulling a streetcar with people?
Clearly, an alternative mode of transport that could confidently tackle the city's terrain was needed. And the solution has since become one of the most iconic urban railroads on the planet. The San Francisco Cable Car. Standing alongside the Golden Gate Bridge as a symbol for the city, cable cars have been running up and down some of California's steepest streets since 1873. And in the 100-plus years since its opening, this remarkable railroad has been declared a National Historic Landmark.
The cable car is a perfect fit for San Francisco.
It's an achievement that's thanks to the work of inventor Andrew Halliday. And keeping his seemingly impossible railroad moving depends on an impressive engineering operation.
Right now, we're in the cable car powerhouse. This is the beating heart. This is what operates the entire cable car system that allows all the cars to move out on the street. The cables range anywhere from 2 to 4 miles, and they're all driven by these electric motors that are 750 horsepower each. And it's all being held with this cable.
Running at a constant speed of 9.5 miles per hour, these huge cables travel out under the city streets in a giant continual loop.
Once the cables leave the barn, there's a series of thousands of pulleys underneath the street. And the cable will ride on those pulleys underneath the slot of the rail.
Remarkably, it's a system that works in the same way today as it did more than a century ago.
Since the day it's been open, we're still utilizing the same processes and techniques that have been handed down from generation to generation to the entire staff who's doing today what somebody did over 140 years ago.
But those beautiful cars are about more than just appearance. And the only way to appreciate what it takes to overcome the hills is to take a ride.
Slide all the way down for me, folks. Slide all the way down for me.
Ed's joining his fellow San Franciscans as they climb one of the city's steepest streets.
The only way to move and or stop the car is by the actions of the gripman. He's got all the manual levers from a track brake to a wheel brake to his actual grip that grabs onto the cable, and that's what makes the car propel.
The grip works in much the same way as a vise. When the lever is pulled back, a set of metal jaws or dies close around the cable, gripping it tight. And when the lever is pushed forwards, the cable is released. It's the secret behind how the cars can ascend San Francisco's hilly terrain.
So right now we're approaching Lombard Street on the famous Hyde Hill. This is the hill that's 21% grade. This is the steepest route that we have in the entire cable car system. So right now what the grip operator is doing is he's pulling back on the grip and the dies are clamping onto the cable, and that's what's propelling us up the hill.
But what goes up must also come down.
Hold on, everybody, going down a little baby hill. Nothing major.
And things get even more complicated when a car approaches a crossing.
So what's about to happen is we're going to cross over Mason Street. So what he's doing here is letting go so he can coast over the intersection so we don't run into the other cable underground.
Let go too late, and the operator could hit the cable at the junction and cause an accident.
So now we're coasting over the intersection.
But let go too soon, and there won't be enough speed to clear the crossing.
So now we've re-gripped the cable and we're back on our way.
But wear and tear on the grip system is dramatic. So how do engineers keep this brilliant mechanism functioning over 100 years after its inception? The grip system of San Francisco's cable cars is essential for the railroad to operate around the city. But the toll it takes on the equipment means maintenance engineer Luis Carrazzo is kept busy in the workshop.
This is like the engine, the propulsion system for the cable car. Without this thing, you're not going anywhere. So as you can see, these dies are completely worn out. I got to knock them out of the hinges to put these new ones back in. You're grabbing and releasing the cable. The cable just rubbing in it all day long and just tearing up the metal.
And without these regular repairs, the grip could cause serious damage to the system's other key component.
You got a cable car 6 tons weight. And you remember, it's carrying 6 tons plus the passengers in there. Pretty heavy. Right now, what I'm gonna do, I'm gonna completely disassemble it.
For Luis, this is nearly non-stop work, with a set of dies needing changing every 3 or 4 days.
We got brand new dies right here. They're ready to put back on into the grip.
But without it, the cable cars simply couldn't function.
So this work, definitely vital. I can take it apart, put it together in the morning, and by the afternoon, it could be worn out. And it is just a part of the cable car daily runnings. We have to get it done.
Thanks to the work of Luis, and many more like him, day after day, this iconic city railroad keeps running up and down the streets of San Francisco, defying all the odds.
I mean, if you look behind us and you can see the hills and the grades that we have to deal with and how steep everything is, the cable cars were designed to be able to get through that treacherous terrain.
And there's little doubt that the cable car system is one of the most incredible pieces of urban railroad engineering ever constructed.
It still stands the test of time today. 140 years later, we're still operating on the hills. There's no way I could ever understand or fathom what the city would be like without it.
London at the turn of the 20th century. In just 100 years, England's capital experienced a rapid rise in its population, growing from less than 1 million to over 6.5 million. Under the strain of this hasty expansion, in a scenario similar to today's most congested cities, getting around became a serious problem, as physicist Andrew Steele is experiencing for himself.
In the early 1900s, London was one of the largest and most populous urban areas in the world. And just like today, congestion was a real problem. You can easily imagine these vans being replaced by horse-drawn carriages, but the problem is pretty much the same. It's not about how many horsepower you've got if you're just stuck in traffic like this. Been in this cab about 20 minutes, and I don't think we've gone a mile. This is why I cycle around town normally.
But it wasn't only commuters that were suffering the consequences of the backed-up traffic. London's postal service relied heavily on the roads. But with mail coaches barely managing a crawl, the deliveries were suffering severe delays.
In those days, one of the most important ways to communicate was by post. And with sorting offices spread across London, the post office was going to have to find a faster and more efficient way to get that mail around town if the capital was going to stay connected.
Today, Andrew is en route to discover how one pioneering railroad helped keep the lines of communication flowing.
The solution the post office's engineers came up with lies down here, 20 metres below the city's crowded streets.
In 1927, one of the most unique railroads the world had ever seen launched.
Check this out. This is what they came up with, the London Post Office Railway. What an amazing contraption.
The world's first driverless electric railroad. These miniature trains rode an underground network of almost 22 miles of track at speeds of up to 29 miles per hour, serving 8 stations and sorting offices. For 3/4 of a century, it ran uninterrupted, carrying up to 4 million letters a day, and London hardly even knew this ingenious system existed.
This is so impressive. I've lived in London for years, and I had no idea that all this was down here, let alone that it was still running in 2003, delivering letters right across London. This place is now just a tourist attraction, but back in 1927, when it was opened, it was a real engineering pioneer, allowing it to run for an astounding 22 hours a day, delivering millions of letters all across London.
But constructing this urban railroad and its labyrinth of tunnels was no small feat. Built in the early 20th century, well before modern tunnel boring methods, it would take an innovative engineering strategy to get London's mail rail up and running.
Wow, what an amazing place to be. We're going deeper underground, and it's really quite cramped down here. Imagine the workers excavating these tunnels. It must have been grueling work, and also not a job for the claustrophobic.
Underground tunneling in London was by no means a new concept in the early 1900s. But the early work on tunnels for the tube network had been an arduous and dangerous endeavor, thanks to the challenging conditions. The layer of soft clay beneath London meant water could seep in, potentially causing tunnels to collapse.
The post office were building over 20 metres below the streets of London, and so they needed this tunnel excavation to be quick and efficient, but most importantly, safe for the workers doing the excavating.
The innovative solution to this problem came from one of tunneling's great pioneers, James Greathead.
The solution the engineers used was called the Greathead Tunnel Shield. It worked a bit like this cookie cutter. So imagine I'm trying to build a tunnel going towards you in this material here. What we can do is place our tunnel shield in position, shove it forward with a series of hydraulic rams, and as this cutting edge dislodges material, workers inside can excavate it, safely protected by the shield. Then, as it moves forward a bit further, we can start constructing the lining of the tunnel behind the shield as it moves, making the whole process fast and efficient, and most importantly, safe for the workers who are protected inside here.
This groundbreaking technique not only made it possible to build this railroad, it also enabled the London Underground to dig much deeper, heralding the transformation of London's transport network. It took 3 years to dig the tunnel system for the Post Office Railway. Construction was halted when World War I broke out. But in 1927, with the rails laid, this innovative electric railroad finally started operating. However, London's postal system would encounter another problem, one that threatened to derail the whole project.
The route between the stations was essentially a giant loop, and as you can see, the corners could get pretty tight. Now, in the original design of the trains, the wheelbase, so the distance between the wheels, was about 2 meters. So let me show you what that means by getting out this tape measure. You can see with this straight tape measure laying on the curve, it's just not following the track at all. What that meant was that there was a lot of wear and tear on the wheels, on the track itself, and in the worst case scenario, trains could get derailed, get stuck, and that could stop the whole network entirely. Now, derailed train is really bad news for those letters and parcels making it to their recipients on time. So what was needed was some kind of engineering solution to allow the trains to navigate around these difficult corners.
If the engineers were to keep their trains on track and deliveries regular, they would need to go back to the drawing board and redesign them from the wheels up.
This stuff's all just been down here pretty much untouched since 2003.
To see the solution engineers devised, Andrew has been given special access to where the Post Office Railway's fleet has been stored for decades.
This is the new design, and so the first thing we can do is get out the tape measure again to measure this distance here between the wheels. It's about 1.30 meters or 1.40 meters, so much shorter. And the other big innovation is that this is connected into what's called a bogie, and it's made up of this big wheel here, which is the drive wheel, which is directly connected to the electric motor, which is underneath this section here. And then we've got this smaller wheel here at the back, which is connected to carry the weight of that carriage. And that means that this long carriage here is able to be articulated to rotate around this point, which is known as the kingpin. And that meant that these trains are much more flexible when it comes to going around tight bends. Additionally, it meant you could have a much longer carriage in between these bogies. This new design came with a number of significant advantages. Firstly, there was less wear and tear on the wheels and the track. Secondly, there was less chance of derailments. And thirdly, these lovely long carriages meant that we could carry more post beneath the streets of London.
Solving this final engineering puzzle enabled the Post Office Railway to run successfully for 76 years, reducing travel time across the capital, and in the process, alleviating congestion on London's busy streets.
This is pretty cool.
In the 20th century, this was a game changer for the capital, a hidden hero working tirelessly below ground to keep London on track. Hamburg in northern Germany. Despite being positioned 68 miles inland, incredibly, this leading city of international trade has grown and thrives from its busy port, Europe's third largest.
It's hardly any distance at all from the centre of the city of Hamburg, and yet there's this huge dock.
Connected to the North Sea by the Elbe River, Hamburg links Europe with trade from East Asia and the Baltic region. But this port became so busy that its infrastructure began to struggle. In order to keep up with the sheer volume of freight coming in, engineers decided to create a rail network like never before. Hamburg is one of Europe's busiest ports, and as the volume of cargo has exponentially increased, the city's resources have been strained. To deal with the escalating needs of the port, engineers have created a remarkable rail-based solution.
The sheer scale of this place is just incredible. It's taken us 5 or 10 minutes just to drive from one end of this terminal to the other.
In 2002, they opened the Altenweder Terminal, the largest container rail terminal in Europe.
Looking around this port, you can see the crucial importance of rails, not just for the trains that ultimately take a lot of the goods out of this place, but for all of the operations inside the port. Everything is running on rails. Everywhere around me, there are these giant cranes constantly. Everything's bustling, moving these containers off the ships onto the land, and then replacing them with new containers from over there, keeping this whole port moving. The real secret to this place's enormous efficiency is these things. And we've got a rail, looking much more like a conventional railway. But the thing that's weird about this is we've just got one. And if we were to imagine this as a train track, it has a ridiculously wide gauge because the other rail is somewhere over the other side there. This is an RMG, or a rail-mounted gantry. And what this allows it to do is move this huge crane system up and down along this massive stack of containers and access any one of them.
Historically, both the port and city have grown in tandem, with a road and rail network to distribute the cargo. But in recent years, a combination of ships getting larger and a global increase in the use of containers has led to a massive rise in the quantities of cargo moving through the port. For sales director Thomas Lutia, keeping the freight moving is critically important.
Hamburg is one of the busiest industrial areas we have in Europe. 1990, we had a number of about 2,000 containers which were loaded and discharged. Now we discharge up to 40,000 of those containers.
And by 2030, the volume of containers that the port will handle is predicted to increase by a further 43%. But located in the heart of the city, the port has limited space for expansion, leaving no other option but to find a way to handle the freight more efficiently.
A truck, it can carry 2 of those containers. A train carries 100. So we need to use the capacity which we have in German and European hinterland best, because we will not get new train tracks, new motorways. We have to use them better than before. And the answer for that, for us here in the north, is the railway. When we started with this facility, CTA, 16 years ago, this was the first fully automated terminal, and I tell you, in the first years, everybody was laughing about us. Now it's standard.
This high-tech terminal has the capacity to handle cargo from 4 ships simultaneously and distribute it onwards into Europe, either by train or truck.
Railways have long been integral to the distribution of freight once it comes off ships. But what's surprising is that as soon as this ship hits the quayside, it's immediately confronted by rails.
Container handling is divided into 2 stages. The first is at the waterside and is the only part of the process that requires a human crane operator.
Just look at the size of these cranes. These things are called ship-to-shore cranes for the obvious reason that they move the containers off the ships and onto the shore, and they are gigantic. If that top beam gets tilted up to its maximum height, it can reach over 100 meters in the air. They're called dual trolley because the top trolley there brings the container off the ship down to this level here, where a second trolley moves it onto some automated vehicles over on the other side. They are incredibly efficient and move huge, huge numbers of containers.
But getting the cargo to shore is only half the battle. The next part of the process is why the Altenweder Container Terminal is known as one of the most technologically advanced in the world. The Altenweder Container Terminal in Hamburg is, in itself, a massive engineering accomplishment. When a vessel first comes to port, enormous ship-to-shore cranes move the containers to land. 2 remotely controlled cranes working at different heights along a stack of containers, taking them to and from automated vehicles.
Mounting these RMGs on rails is an incredible example of engineering efficiency. This whole thing is controlled by software. The software says which containers are going to be pulled out, which trucks are going to be here to receive them, and it makes sure that this enormous operation can run smoothly and efficiently.
The Port of Hamburg's bold use of technology has transformed the way the port and the city operates, with billions of objects connected to a computerized system via intelligent sensors.
The degree of automation here is just astonishing. You've got these thousands of transponders sensing the location of every one of those vehicles, not a single human being. And those things, there are some that are electric, there are some that are diesel-powered, and when they run out of batteries or run out of fuel, they can automatically drive themselves to the filling station or to a different station that swaps out their batteries and gets straight back on with their work.
This groundbreaking solution to handling cargo means that the port can now handle over 7 million containers per year, setting new global standards. In 2017, 58,500 freight trains passed through Hamburg Railport, transporting vital goods to its city and beyond.
This port is just such an impressive operation, and the whole thing is running on rails. To bring the goods onto this train track below me and transport the cargo all around Europe. It's just incredibly efficient, all of it choreographed by software. And without rails, that just wouldn't be possible.
Since the invention of trains, the cities of the world have given engineers some of their toughest challenges. Inspiring, daring solutions.
Yeah, the cable cars is the backdrop to everything San Francisco, and the grades that the cable cars overcome. It's amazing to think that everybody can enjoy and get around the city.
And groundbreaking innovations.
Nearly everything you buy, from food to clothes to cars, is shipped in these giant containers on these enormous ships. And without rails, none of this would be possible.
To create impossible railroads.
While not impacting the everyday operations of the New York City passengers, we have been building one of the largest civil projects in the history of North America.